In this video, we'll talk about calorimetry, which is the study of reactions to determine the heat of reaction or the molar heat of reactions. So thermochemistry is derived from two words, thermo, which means heat, and chemistry for chemical reactions. So thermochemistry is the study of energy changes in terms of heat by a chemical system during a chemical reaction. In order for us to study thermochemistry, we require three things: an isolated system, which means that energy or matter cannot escape. All energy and matter is accounted for. We must have carefully designed experiments, and we have precise measurements. The design experiments must capture all the energy loss or gain by our chemical reaction. And we must measure these precisely using a thermometer as well as a graduated cylinder. It is not necessary to use something as precise as a pipette. In high school thermochemistry experiments, we will use what's called coffee cup calorimeters because it affords us the precision necessary to study the reaction at a reasonable cost. While calorimetry is the study of energy changes in a reaction, we will use a calorimeter to study these changes. A calorimeter is an instrument to measure the amount of energy lost or gained by a chemical reaction or a phase change. In here, we have a picture of a coffee cup calorimeter. The reaction will happen inside the coffee cup, and we'll measure the change of the water temperature in the coffee cup using a thermometer. Now, this system has two parts: your chemical system, so your chemical reactions, as well as the calorimeter, which is considered the surroundings. And we'll measure the change in temperature of the surroundings in order to determine the change in energy of the chemical system. In high school, we will often use water as our surroundings because it is easy to determine the temperature of water, and water has a high specific heat capacity, so it is useful for many reactions. The key concept behind a calorimeter is that energy loss or gain by our chemical system will be transferred to the surroundings, and we can easily measure the temperature change of a surrounding. In a typical high school calorimeter, the chemical system is surrounded by the water, and we can easily measure the temperature of the water using a thermometer. If a reaction is exothermic, the water will be hotter, so then the energy is absorbed by the water. However, if a reaction is endothermic, the water will lose energy and it will become colder. Again, to re-emphasize the point, if the increase in temperature of the water indicates that the energy was gained by the water or lost by the chemical reactions. Therefore, the chemical reactants have lost energy. So therefore, the reaction is exothermic. If the temperature of the water decreases, the reactants have gained energy, or you can say that the products of the chemical reactions have gained energy. Bottom line is that energy lost by the chemical system is gained by the water, or energy gained by the chemical system is lost by the water. It is like a teeter-totter. When one system gains energy, the surroundings will lose energy. If the system loses energy, the surroundings will gain energy. If you recall from earlier lessons, the total energy of an object, it's this total kinetic energy of all the molecules, of all the atoms in that substance. Remember, temperature measures the average energy, whereas thermal energy measures the total energy. The way we measure the change in the thermal energy of an object is using the formula Q equals mc delta T, which we briefly did in Science 10. Here, Q represents the quantity of heat or energy, it can be measured in joules or kilojoules. M is the mass of the object, most often in grams, but we can also measure it in kilograms. Delta T is the change in temperature in Celsius, and C is the specific heat capacity of the substance that has lost or gained energy. Well, what exactly is specific heat capacity? It is the quantity of energy, measured in joules, required to raise the temperature of a unit mass, for example 1 gram, by 1 degree Celsius, which is also the same as 1 degrees Kelvin. Here we have a table of specific heat capacity values. You'll notice that water has a relatively high specific heat capacity of 4.19 joule per gram per degree Celsius. So therefore we often use it in our calorimetry experiments. Remember, specific heat capacity varies for different substances and even for different states. So for the specific heat capacity of ice, which is frozen water, it is much less than liquid water. Same thing for steam. The specific heat capacity of steam is about half of that for liquid water. Let's look at a quick example. We are told that the specific heat capacity of a rock is 0.9 joules per gram degree Celsius. Calculate the energy loss if 500 grams of the rock drops in temperature from 70 to 25 degrees. Here we have our C value. The mass is 500 grams. We do not need to change the units because our specific heat capacity is given to us in grams. If it was not, we would need to change it into kilograms. And lastly, the temperature changes from 70 degrees to 25. So our delta T is our final temperature minus our initial temperature. So it's 25 degrees Celsius minus 70 degrees Celsius, or negative 45 degrees Celsius. Here is our formula. Q equals mc delta T. M is 500 grams. C, we were given, is 0.9 joules per gram degree Celsius. And our temperature change is negative 45 degrees. We do our math, and it becomes 20.25 kilojoules. Rounding for sig digs, our final answer is negative 20.3 kilojoules. This number is negative because the rock has lost energy to its environment. If you're losing money, you have a negative bank account. Here the rock loses energy, so it has a negative value. Let's look at a simple calorimeter. In our high school labs, we're going to use coffee cup calorimeters. It consists of 3 styrofoam cups, a lid to keep the heat in, a measured quantity of water, usually about 100 or 200 milliliters, and a thermometer to measure the change in the temperature of the water. Now remember, because this is a water-based reaction, all of the reactants must be soluble, must be dissolved in the water. And then the energy lost from the chemicals in the reactants will be gained by the water if it's an exothermic reaction, or the energy gained by the chemicals will be coming from the water, or if it's an endothermic reaction. There are 2 assumptions that are undertaken when we use a simple calorimeter like this. Is that the heat lost by either the surrounding or the system will be transferred as to the heat gain by the opposite. Another assumption is that it is a closed system, which means energy does not escape from our styrofoam calorimeter. A more complex calorimeter is a bomb calorimeter. Here, the reactants are placed inside what's called the calorimeter's bomb, which is surrounded by the calorimeter water. Inside the bomb, it could be purely air. So for this type of calorimeter, we could study gaseous environments or solid reactions. Any temperature change caused by the reactants will be transferred to the water. It is essential that we have a stirrer to move the water around to make sure an equal mixing of the water molecules so that there's an efficient heat transfer from the bomb to the water surroundings. Once we have all the reactants in the bomb calorimeter, we can start the reaction using an electric spark or some sort of other starting device. Because of its complex nature, we will not be using this in high-school experiments. Before we continue any further, let us talk about the assumptions behind a calorimeter. Again, all of the energy lost by the system is gained by the calorimeter or the surroundings. The material of the system is conserved. There is no loss of matter, such as a gas. The specific heat capacity of the water over the temperature range is 4.19 joules per gram degree Celsius. So the water is neither freezing nor boiling because that involves a different specific heat capacity. The specific heat capacity of the dilute aqueous solutions in which our chemical reactants are dissolved is also 4.19 joules per gram degree Celsius. The density of the solution is still 1 gram per milliliters, the density of pure water, and that the thermal energy loss or gain by the calorimeter is negligible. That means that the styrofoam cup, the thermometer, any mixers does not absorb or gain any significant amounts of energy. If all of the assumptions are true, then we can say that the total energy change of the chemical system is equal to the total energy change of the calorimeter surroundings. So let us look at an energy diagram for a reaction. Here we have the reaction of zinc with hydrochloric acid to produce hydrogen gas with zinc chloride. From previous experience, we remember that this is an exothermic reaction. The products will feel hot to the touch. So if we're to look at the energy of the reactants, here they have high potential energy. However, after the reaction, they will have lost energy to the water, so that their energy is now lower. On the other hand, however, the water initially had a low kinetic energy, but they gain all of the energy lost by the chemical reactants. So at the end, they have a high kinetic energy, or a high temperature. Because the reactants have lost energy to their surroundings, this can be considered an exothermic reaction. So once again, in the reactants, they had low kinetic temperature or low energy, but they had a high potential energy. After the reaction, the compounds have high kinetic energy or high temperature, and they have a lower potential energy. The loss in potential energy is matched by the gain in kinetic energy of the surroundings. When we talk about calorimetry problem, we can think of it as two parts. The first part is the chemical reaction, or our system. To determine the energy change of a system, we can use a delta H calculation, which we'll do in a couple of slides, or we can determine the change using the formula mc delta T if this is an aqueous mixture, aqueous reaction. On the other hand, the calorimeter side, or the surroundings, we will always use the formula mc delta T, or if we're not given the mass, C delta T. And however, this may be 2 or more steps if we have to consider the water in the calorimeter plus the metal, or a combination of the both. And remember, the only connection between these two sides, between the system and the surrounding, is the amount of heat transferred. The amount of heat lost by the system, by the chemical system, is equal to in number, but in opposite sign, to the amount of heat gained by the surroundings. So here, if the reaction side loses 1.9 kilojoules, then the calorimeter, or the surroundings, must gain 1.9 kilojoules. Let's look at a simple calorimeter example. Here we have a cold copper spoon. We've put it into 500 milliliters of water that is in the styrofoam calorimeter that was originally at 90 degrees Celsius. After the system has come to an equilibrium, the final temperature of the system is now 88.5 degrees. And we're asked to find the original temperature of the spoon. Here we have our equation, Q spoon equals Q water. For our example here, we can consider the spoon to be our system and the water to be our surroundings. So any heat lost by the water is gained by the spoon. To determine the amount of heat gained by the spoon, we're going to need to use the formula Q equals mc delta T. So we can substitute mc delta T for Q spoon. And to determine the amount of heat lost by the water, we're also going to use mc delta T. However, the masses will be different. So now we can substitute. We know that the mass of our spoon was 100 grams, and we're told, using a table, that the specific heat capacity of our copper spoon is 0.385 joules per gram degree Celsius, and we're asked to find the temperature. On the right-hand side of the equation, we're told that we have 500 grams of water, because 1 milliliter of water is equal to 1 gram. The specific heat capacity of water, looking at our data table, is 4.19 joules per gram degree Celsius. And the change in temperature is 90 minus 88.5 degrees Celsius. And then now we can solve for the change in temperature of our copper spoon. Doing that, we find that it is equal to 78.9 degrees Celsius. However, we have to take that into account that this is the change in temperature of the spoon. So the original temperature, or Ti, is really 88.55 degrees, that's our final temperature of the spoon, minus 78.9 degrees, which is equal to 9.6 degrees Celsius. So the temperature of our spoon initially was 9.6 degrees. Here we have done all the math in one step. However, if you're more comfortable in doing the math in two steps, that is, finding an amount of heat lost by the water and then equating that to an amount of heat gained by the spoon, that is perfectly acceptable too. In our last example, we used our calorimeter to measure the physical change of a substance. However, we can also use it to measure the chemical change of a different substance. When we talk about chemical change, we're talking about the enthalpy of a reaction. It is the energy change for the whole chemical system when the reactant changes to products. The symbol for this is delta lower subscript r capital H, and the units for this are in kilojoules. A very similar measurement is the molar enthalpy of reaction. Here the symbol is delta subscript r H subscript m. The m indicates it's per mole. It is important to do this because we can often use different amounts of chemicals, but if we standardize it to a mole, we can communicate our results more clearly to other scientists. The units for this is now kilojoules per mole, because again, it's a per mole, quantity per mole, just like molar mass, where it was grams per mole. This table shows some of the symbols used when we talk about enthalpies of reaction. If it's a subscript R, it means any reaction. If it's a C, it's a complete combustion. F stands for formation. D is decomposition. SOL means the heat of solution, the enthalpy change when something is dissolved in water. And DIL is dilution, because when an acid is diluted, it often involves an exothermic reaction. Let's try and do an example. What is the molar enthalpy of combustion of propane if burning 0.52 grams of fuel increases the temperature of 175 ml of water in a 12-gram metal calorimeter from 10 degrees to 45 degrees? So here we're looking for the molar enthalpy of combustion, which is the delta R H M of propane. Propane, if you recall, is 3C3H8, and the molar mass of that is 44.11 grams per mole. Our very first line, we need to set up our overall equation. Remember, the energy lost by the system will be equal to the energy gained by the surroundings. So the change in enthalpy of the propane reaction is equal to the quantity of heat gained by our calorimeter. Substituting the molar change of propane with N times the delta CHM. Remember, delta CHM is the molar enthalpy of combustion. And on the other side, the calorimeter side, we can replace Q of the calorimeter with MC delta T of the water plus the MC delta T of the metal calorimeter. The number of moles can be determined by 0.52 grams divided by the molar mass. Our molar enthalpy of combustion is unknown. We can replace M of water with 175 grams. The specific heat capacity of water is 4.19. And the temperature change went from 10 degrees to 45 degrees, or the change is 35 degrees. The mass of the metal calorimeter is 12 grams, and we're told the specific heat capacity of a calorimeter is 0.7, and the calorimeter also changed in temperature by 35 degrees. Simplifying all the numbers, we have this equation. We still have our unknown, our molar enthalpy of combustion. Let's take a look at the units. On the right-hand side, we have the units of joules or kilojoules, and on the right-hand side, we have units of moles. In order to fully isolate for delta H of combustion, we have to take kilojoules divided by moles, so that our final answer, the molar enthalpy of combustion, has the units of kilojoules per mole. Also notice that while we have a positive number in this step, our final answer should be negative, because in a combustion reaction, the products of the reaction have a lower potential energy than the reactants. It is an exothermic reaction, therefore the delta H should be a negative number. You may wish to pause the video now in order to examine all the numbers closely. Let's look at another example. When 50 milliliters of 1 mole hydrochloric acid is added to 75 milliliters of 1 mole per liter sodium hydroxide, the temperature of the calorimeter, of the water in the calorimeter, changes from 20.2 to 25.6 degrees. We're asked to find the molar enthalpy of neutralization for the hydrochloric acid. That is, we're asked to find the heat of reaction for the neutralization of the acid, delta R H subscript N. We'll indicate that on the left-hand side of the reaction. On the right-hand side of the equation, we have the heat change in the calorimeter. We can easily substitute that with MC delta T for the water in the calorimeter. On the left, we have N times our unknown variable. N can easily be found because, if you remember from solution chemistry, N is C times V. So we have a concentration, 1 moles per liter, times our volume, 0.05 liters. Here is our unknown molar enthalpy of neutralization. On the right-hand side, the total mass of the water is 50 milliliters plus 75 milliliters, 125 milliliters. That is represented here. The specific heat capacity of water is 4.19, and the change in temperature went from 25.6 degrees to 20.2 degrees. Simplifying everything on the right-hand side, we have 2.828 kilojoules. On the right, we have 0.05 moles times delta HR. And if we're to divide 2.8 kilojoules by 0.05 moles, we'll have 56.565 kilojoules per mole. However, once again, this number should be a negative value because the surrounding, the water, went up in temperature. That means our hydrochloric acid and sodium hydroxide lost potential energy, so the delta H value should be negative. Once again, you may wish to pause the video and analyze the numbers in further detail.